Hello, welcome back to Physics Chapter 7, Waves and Sound. This and the next chapter are probably the biggest parts in physics that will be tested on the MCAT. Well, that isn't saying much because physics isn't a huge part of MCAT in proportion anyway, but here we go. V equals the velocity equals frequency times the wavelength. You might see this in a different form of the speed of light, c instead, but this is a generic form. Speed of wave equals the frequency times the wavelength. And the reciprocal of frequency is the t. So that is just the time, and that can be expressed in 1 over f. And you can also use angular frequency to tell. So pendulum, the big thing is pendulum. When it swings, you can tell its frequency of swinging. Next is the sound. The sound longitudinal wave. There's two types of wave. There's a longitudinal wave and a transverse wave. Sound is a longitudinal wave because it's compressing air from one to another, and you can determine the velocity by its bulk modulus divided by density, rho, and rooting it. Now, speed of sound in air is about 343 meters per second. Now, let's focus on the Doppler effect. The Doppler effect basically is thinking about the speed of sound will change, and the frequency, the perceived frequency, will change based on the moving objects as well as moving receivers. So let's look at this equation. The perceived change in frequency, the new frequency, is equals to the original frequency multiplied by the speed of sound, v, plus or minus vd, the detecting velocity, which the detector is like me hearing it. It's you're traveling, divided by the velocity of sound, minus or plus the velocity of the source. So if when moving towards the other, the frequency will go higher, and we use the upper sign. And when you use the lower sign is when you're moving away from the other. What does this mean? Well, detector, let's call that the ambulance. Call that me in a car here. And the source is ambulance sound. When ambulance is approaching from behind me, it's going much faster than I am. So it's approaching me. So in the source, it would be using up. So minus sign. And since I'm moving away from ambulance, I'm using the negative sign. So both are negative, but the denominator, the velocity vs, is moving much faster than mine. So the overall denominator is going to get much lower, and that's going to increase this frequency. So my new perceived frequency is higher than the original one. Conversely, if I'm traveling towards ambulance already passed me, but it's still speeding away. Although I am moving towards ambulance, plus in the numerator, the denominator, ambulance, is plus and moving away. So the denominator gets a lot more bigger. And since the source is a lot bigger than me, the perceived frequency is going to decrease, and the perceived frequency will be lower. So you hear ooh, ooh, ooh as you're moving away. Okay, now let's look at the string. The string part of the wave is much simpler because you can actually visualize it. When you visualize a string and just walk it up and down, like a mouse, ooh, we have what's called an antinode, where it's the peak and the trough, versus the node, where it doesn't move, right? It stays at that one place. That's a node. When you move this wave up and down, we can determine the wavelength, because this is only half of an entire wavelength, right? If you know sine wave goes all the way like this. This is only half of a sine wave. So the wavelength equals 2 times the length divided by n, where n could just be 1, 2, or 3. Keep going on and extend the length. Now, if you want to go into second harmonics, for example, over 2, and that just becomes length. So using the same length, you actually wrap it even faster to generate a wavelength, a larger wavelength. Okay. Sorry, you make a smaller wavelength if you have a faster frequency. My bad, because they have to be, if one goes up, one will have to go down. Alright, now if you put the sound through a pipe, open pipe, it's going to behave the same as a single transverse wave, in that you use wavelength equals 2 times the length divided by n, because this, think about the cosine, right? This is only half of the cosine. You need to finish up this wave. So n, 1, 2, 3, and so forth. So you can increase the harmonics, the fundamental, and then you can go to the second harmonic, third, so on. Yeah, open ends will always end the antinode, the peak and the trough. But closed pipe, where one end is completely closed, it forces the air to go down the other way, and one end is the node, because it cannot change here. So that is a little different, because this little thing is only 1/4 of an entire wavelength. Like you're gonna go up into a peak, but you didn't go down, and you go down and go back up. So this is only 1/4 of a length. So to get a wavelength, you need to times the length of this tube by 4, and then divide by n, where n equals 1, 3, or 5. You can only go this multiplied by 3, divided by 5. You can't end in 2, because if end in 2, it will be node, and that can't happen in a closed pipe. Right, so you will just need to follow the formula, 4 length divided by n. You can also manipulate around to use a frequency, right? Just use some little manipulation in algebra, it should be fine. Intensity can be calculated by the power divided by the area. So the greater area, the intensity gonna be dispersed, right? Because the area is large and disperses the energy by large amount. And it's also equals to amplitude squared. So if you increase the amplitude, this antinode up just a little bit, double it, you're gonna quadruple it, the intensity. Now last thing, we also want to calculate the decibels, and decibels, every time you increase the decibel by 10, you increase the intensity by 10 times. So a jet engine is 10 to the 6 times greater, so 1 million times louder than a blender, for instance, but it's only 60 decibels higher. So each 10 decibels is a power of 10 greater. And that's pretty much it.